So hello everybody. Welcome to the last One World Mind seminar of the year. So we'll be back on January 7th, but otherwise you shouldn't be too sad or happy, or you should definitely be happy, let me put it that way, because we have an excellent final speaker for the year. So today we have Associate Professor at Carnegie Mellon University, David Woodruff, is going to be talking to us today. He has a lot of influential papers on algorithms for massive data sets and streaming algorithms for data intensive problems, and a lot of great work work of his that I'm the biggest fan of probably is randomized numerical linear algebra and sketching techniques for numerical linear algebra problems. And so I am very happy to see what he's been up to recently. And so I will turn him over to give us a sketch of his research.
Okay, yeah, thanks very much for the introduction and for inviting me, and thanks for everyone to everyone for coming. Yeah, the title is a very sketchy talk, and what I wanted to do is go over the technique of sketching or dimensionality reduction and a large number of its applications to problems in machine learning, numerical linear algebra, and optimization. So, yeah, so here's the outline for the talk. First, for those who haven't seen usages of sketching before, I'll quickly show how it can be used to solve least squares regression, and in that process, go over the sketch and solve paradigm that I like to call it, together with different matrices for dimensionality reduction. I'll then discuss other kinds of guarantees you might want from regression, guarantees on the solution vector, maybe high precision guarantees. And then I'll discuss a wide range of variants of regression, ridge regression, robust regression, kernel regression, tensor regression, and structured problems. And with whatever time I'll have left, I'll also go into solving the low rank approximation problem, or singular value decomposition problem, using sketching, and show a bunch of variants of that. So how to solve the column subset selection problem, also for general loss functions, and in context of tensors, weighted low rank approximation, and structure preserving low rank approximation. So let me just go ahead and get started with regression here. So here is the bread and butter of statistics, the least squares regression problem. You have an n by d matrix A, and as input, you can think of the n rows as examples and the d columns as features in some problem. And you're given an n by 1 vector B, and you just want to find a d-dimensional vector x star that minimizes the Euclidean distance between A times x and B. Okay, so in this simple example here, you just want to find a line that fits these points well. And so you can think of the coordinates of B as what you observe, and the corresponding row of A inner product your vector x as what you predict, and you're trying to minimize the sum of squares of differences. So this is a very simple statistical model, but still often very useful, and it has a number of nice properties. One of those is that it has a closed form solution. So if the columns of A are linearly independent, I can write down the solution x star as A transpose A inverse times A transpose B. And the issue that I want to point out here is that for large data sets, the time for computing this closed form solution is nd squared. Okay, so I have to multiply this n by d matrix A by this d by n matrix A transpose, and that's kind of the bottleneck here. I mean, you can speed it up using theoretical algorithms for fast matrix multiplication, but still this is very slow, and it motivates coming up with faster solutions. So can we speed this up by using dimensionality reduction? And here is the sketch and solve paradigm. So we first relax the problem. Instead of solving the regression problem exactly, we're going to allow ourselves to output the solution vector x prime, for which the least squares cost of using x prime is at most a 1 plus epsilon multiplicative factor times the optimal least squares cost. Okay, and we allow for randomized algorithms. Okay, so here is the what I'm calling the sketch and solve paradigm. So the way to solve this is, let's think of A here as being a very tall and thin matrix. Okay, so it's n by d. N is much larger than d. This is the over-constrained case. And what we want to do is we want to squash our regression problem down into something much smaller so that we can solve it more quickly. And the idea here is to draw a random matrix S, which is going to be a wide and fat matrix. And there are many different random families of matrices you can choose. But what's important is the number of rows, k, is much smaller than n. And what you do is you compute S times A. When you do this, this takes this tall thin matrix A and squashes it down to roughly a square matrix. Okay, so think of K as being something about D, the smaller dimension. And you also compute S times B, so you squash this n-dimensional vector B down to a, again, a k-dimensional vector. And all you do is you now solve the sketched regression problem where the matrix A has been replaced with S times A and the vector B has been replaced with S times B. Okay, so you can solve this problem, say, using the closed form solution that I gave to you on the previous slide. And importantly, this small problem no longer depends on this large dimension n. Okay, so it's much faster now to compute that closed form solution. And the hope is that for appropriate choices of this random matrix S, if you take the solution X that you get to this sketch regression problem and plug it back into the original problem, that you get a nice approximation with good probability. Okay, and so the natural question here is, well, how do I choose the sketching matrix so that this sketch and solve paradigm works? And it turns out that lots of choices for this matrix S work. So maybe the first thing that might come to mind is a matrix of IID normal random variables. Okay, and in fact, this does work. And this small dimension k, so remember S is k by n. It's short and fat, and the small dimension k is d over epsilon squared. And if you compute SA and SB, you'll get a 1 plus epsilon approximation with high probability. The only issue here is, well, our goal is to improve the running time of regression, and we have to compute S times A, which is problematic if S is a dense Gaussian matrix. Computing S times A is going to take, if S is k by n, actually, can I draw here? I don't see an annotate option here. Okay, well.
There might have been a pen right underneath that, but it's okay.
A pen here? Okay, but the usual annotate here in Zoom is missing, or am I missing something?
Yeah, the annotation might be turned off to prevent other people from annotating your slides.
Oh, okay. All right. Well, I can try this.
Sorry.
Haven't used this before, but yeah. So okay. So okay. Let me not do that. That's not working. That's just a laser pointer pen. Okay. Yeah. Okay. So here is remember S. This is S. It's k is d over epsilon squared by n, and you're multiplying it by this tall thin matrix A, which is n by d. And naively multiplying these takes the product of the dimensions time, right? D over epsilon squared times n times d. So this is where the time is coming from. And if you recall the closed form solution, you can actually compute that in nd squared time. So this is actually slower and it's approximate, and sometimes it fails. So it's not a good sketching solution, but at least it was shown to work. Let's get this working. Sorry, and how do I stop? Okay, yeah. Okay, yeah. So this inspired the use of a different sketching matrix called the subsampled randomized Hadamard transform, which is used in this context first by Sarlos, and it's a much more structured random family of matrices. So S can typically be decomposed as P times H times D. It's again going to be a short and fat matrix, but the important point is that each of these factors can be applied to a vector very quickly. So D is just a random diagonal matrix, where each entry on the diagonal is independently set to plus or minus 1 with equal probability. So that's very quick to apply, order n time. H is a dense matrix, the n by n Hadamard matrix, but it has a nice recursive structure. So you can compute H times a vector in only order n log n time. And finally, P, when you apply it to a vector, it just uniformly samples k entries, which is in order d over epsilon squared entries. Okay, so this is your small dimension in your sketching matrix. And so importantly, if I apply S to each column of A one at a time, then for each column, it only takes n log n time to apply S. And so in total, I can compute S times A in nd log n time. And similarly, S times B in n log n time. And it turns out that this actually works. So after having computed these, if I then solve this sketch problem with high probability, I'll get a 1 plus epsilon approximation. And so overall, it leads to an algorithm for regression, which is much faster than just computing the closed form solution. The time is nd log n plus polynomial in d over epsilon. It's roughly d cubed time there. So if n is very large, this is significantly faster than nd squared. Okay, so yeah, there's a question, is there any condition on A needed? No, so this is for worst case A, which is which is one feature of these dimensionality reduction techniques. Now that gives you an algorithm for regression, which was nd log n, and sometimes your matrix A is fairly sparse. Maybe you only have order n non-zero entries. And so it's not clear that you even need to spend nd time. And in fact, there are very sparse sketching matrices called count sketch matrices, which again have the same form that they're very short and fat. The small dimension, instead of being d over epsilon squared, is a little bit larger now. It's d squared over epsilon squared, but still independent of this large dimension n. And the really important point about this matrix S is that it only has a single non-zero entry per column. Okay, so the way it works is on each column, I uniformly choose the position of the single non-zero entry, and on that position, I put a 1 with probability a half and a -1 with probability a half. Okay, and I do that independently for each of the n columns. And one way to sort of visualize what this matrix is doing is when you apply it to a vector. If I compute S times a vector, well, you can think of the rows of S as k hash buckets. Okay, and so what's really happening is you're taking the coordinates of x. It's an n-dimensional vector, and maybe the first coordinate goes to this hash bucket, the second coordinate goes to some other hash bucket, and so on. And so each row is just hashing the coordinates to a bucket, it scales them by a random sign and then adds them to what's already in the bucket. Okay, so and surprisingly, at least to me, this actually works, meaning that if you set k to be this and you solve the sketch problem, then you'll get a 1 plus epsilon approximation. And so yeah, okay. The key property here is that S times A is computable in n and z of A time, where n and z means number of non-zero entries of your matrix. And you can see that, right? If I apply a S to a vector, for each non-zero entry of the vector, it indexes one of the columns of S, and there's only a single non-zero entry there. So if I'm hashing to a bucket, I just scale by a sign and send it to that bucket. So it's very quick to compute, and overall, it leads to an algorithm for regression in number of non-zero entries of A, just the time to read your input, plus a low degree polynomial in D over epsilon. And there's some nice follow-up works of Meng Mahoney and Nelson Nguyen. In particular, the latter gives a trade-off. So if I want to improve this sketching dimension of D squared over epsilon squared to something closer to D, then I can do that by increasing the number of non-zeros per column. Okay. So this is optimal in the sense that, if you want to achieve a multiplicative approximation, you do need to read all of your non-zero entries. Okay. Move on. Now, we showed this guarantee in objective function value. Often, what someone might want, though, is that your actual solution vector that you get, so you're outputting this x prime, you might want it to be close to the actual optimum x star. And just by using sketching, you immediately get this kind of guarantee here, which is that the squared difference is at most epsilon squared times the optimal cost over the minimum singular value of A squared. This is not hard to achieve. I mean, it's it's more or less just saying that if you look at this square difference, then by definition, it's at most this quantity where I multiply by A divided by the min singular value of A squared. And now you use the Pythagorean theorem that this numerator is actually equal to, if I want to look at AX prime minus B2 squared, then let me just write it like first. Okay, so pictorially, what this is saying is that this equality in the numerator is saying that, hey, if I have a subspace, which I'm drawing as a line here, A, and I have a point B, and I want to know, what is the distance to AX prime? That's somewhere in the subspace. That's this squared length. Well, the best thing, by Pythagorean theorem, one way of computing this squared length is to first look at this squared length and add it to this squared length. Now, this is the distance of B to its projection onto A. That's this optimal cost. And then I have to add the square distance inside the subspace. That's this cost. Okay, so all I'm using is this Pythagorean theorem for the numerator. And now you just use the sketching guarantee that this difference, because of your objective function, gives you order epsilon A x star minus B2 squared over sigma min squared. Okay, so you immediately get a guarantee in objective function value. Immediately get a guarantee in the distance of your vectors just from an objective function value guarantee. Okay, so yeah, and one thing that we showed is actually if you use the subsample randomized Hadamard transform, you can improve this guarantee to say that every single coordinate in your solution vector x prime is actually close to the corresponding coordinate in the optimal solution. So if you look at this, if you square this, then the difference here is that I have a d in the denominator as opposed to what's up here. But this is just for a single coordinate. So this infinity norm is just the maximum entry. And if I add up over the d coordinates, then I'll get the overall squared two norm, and that will be the guarantee that I previously had. Okay, but this is a stronger guarantee. It says every single coordinate, is close to the optimum. So your sort of error is a flat vector, and yeah. So you might be interested in the stronger guarantee, which is not achievable by all sketches, but for the subsample randomized Hadamard transform, we can show that. Another thing that sometimes people ask about is that the sketch and solve paradigm as presented has kind of a poor dependence on epsilon. So you saw bounds of the form 1 over epsilon squared. And oftentimes in applications in scientific computing and other places, you really want very high precision. And so you might prefer a log 1 over epsilon dependence. And so there's another way of combining sketching, using sketching for regression by combining it with gradient descent. So you use sketching as a preconditioner. And the way it works is as follows. You first choose one of these sketching matrices we've been talking about, S, but you set the accuracy parameter to be a constant, say 1/2. And you sketch and you solve, and you get some initial solution x0. This is the solution x prime. And I've drawn it over here as x0. In parallel, what you do is you have this S times A matrix, and you compute a QR decomposition. Okay, so here we don't need anything fancy. All we need is that Q has orthonormal columns. Okay, and R is any matrix. And the important thing to note here is that if you look at SAR inverse, this equals Q. The important thing is that since Q has orthonormal columns, its condition number is 1. Okay, meaning that the condition number is just the ratio of the max singular value to the min singular value. And so this is a perfectly conditioned matrix, Q. So you see that R inverse serves as a good preconditioner for S times A. But we don't care about S times A, right? We care about A. And and the idea here is, well, why don't we just try to use R inverse as a preconditioner for A? And that turns out to work. So if I look at the condition number of AR inverse, you can show that it's at most 3 times the condition number of SAR inverse. And the 3 is really coming from S being a 1 plus or minus epsilon 0 approximation of all vectors. So if you're curious where the 3 comes from, it's 1 plus epsilon 0 over 1 minus epsilon 0. But I won't get into the details. I mean, you can make this any constant you want. But the point is that the condition number of AR inverse is a constant. So there are many ways to precondition a matrix. I could have taken the QR decomposition of A itself, but that would have been slow, right? Because A has a very large dimension n. So the idea is first sketch it, compute the preconditioner in the sketch space, and just hope that it's a good preconditioner for the original matrix. And it turns out that it is. Okay, so now what do you do? Well, now that you have a preconditioned matrix with constant condition number, and you have an initial solution x0, well, you're all prepped up to run gradient descent now. Okay, so gradient descent will now converge in log 1 over epsilon iterations because it depends linearly on the condition number, and you're starting at a constant factor solution. And I want to mention that when you run gradient descent, you never have to compute A times R inverse. that would have been expensive because R inverse, it's this D by D matrix, and it's sort of could be arbitrarily bad and dense. But in gradient descent, you're always only iterating with new vectors, and so you compute R inverse times that vector and then A times that vector. So you never have to do this expensive matrix product. And yeah, so that's a way of getting a better dependence on epsilon. You solve this problem, you get your solution X, and then you output R inverse X for the solution to the original problem. Okay. We move on then. Yeah, please stop me if you have any questions. So there are a number of other variants for which sketching is useful. One of those is ridge regression. So sometimes you want to penalize the norm of your solution vector X, for the purposes of not overfitting and so on. And so you add a penalty term. Here I've added lambda times the squared length of X, and lambda greater than 0 is just some parameter. And so you can think of equivalently as the squared length of X being restricted. That's what I've drawn here in this ball. And I'm drawing the level sets of the solution costs of this function. And this is where they intersect. This might be the solution, right? So it turns out that these regularized versions of regression, sketching is useful both when A is tall and thin, and also when it's short and fat. Okay, and one thing that's nice here is that you can get a sketching dimension that depends not on the dimension of your data, but on what's called the statistical dimension. So what this is defined to be is the sum over singular values I from 1 to singular values I of sigma I squared over lambda plus sigma I squared. So you see that when sigma I squared is much larger than lambda, you're just roughly counting the number of singular values larger than lambda. And when sigma I squared is less than lambda, well, then you're getting sigma I squared over lambda contribution to the sum. So you're really sort of downweighting the effect of smaller singular values. So this quantity is typically much smaller than, it's always upper bounded by the rank, but it's typically much smaller than the rank in practice. And one thing you can do is in over-constrained ridge regression, you can replace A with S times A, where S is one of these sketching matrices, which has a number of rows which is linear in the statistical dimension. Okay, so it can be very small. And what I mean by you can sketch is if you solve this problem, then your solution will be a 1 plus epsilon approximation when you plug it back in to the unsketched version. And also in the under-constrained case, there's a way of using sketching. In the under-constrained case, A looks like this. There's a way of using sketching here to reduce the number of columns of A. Okay, to reduce this large dimension D now. Sketching is has more limitations in this context, but you can still use sketching with a dependence now on some properties of A. Okay, so it's still polynomial in the statistical dimension, but it depends on the ratio of the max singular value of A to this regularization parameter lambda. Okay, and you can combine these two sketching techniques at the same time. Okay, so you can sketch the left and the right of A, and now just get some tiny problem that depends on the statistical dimension, if you'd like. And I do want to mention that ridge regression has been studied recently in some quantum-inspired algorithms, and this techniques similar to those here are useful for developing more classical numerical linear algebra-based algorithms for these quantum-inspired problems.
Just to check here, you don't have to sketch B also. And
I'm sorry. Yeah, the dimension doesn't even make sense here. Yeah, I'm sorry. There's a B missing here. Yeah, thank you.
Thanks.
Yeah. Okay. Yeah, so now let me move on to robust regression, another variant here, where sometimes since you have this square in your loss function, you pay more attention to outliers than you should. Okay, so imagine that you have all your points are like almost on a line, but there's one point over here. And because you're squaring the difference to the line, you're going to kind of pay a lot of attention to that outlier. So sometimes what you want are loss functions that kind of downweight the importance of outliers. And there are a bunch of them. So one is you could look at the L1 norm as your loss function. Another is called the Huber loss function. And Huber interpolates between least squares loss and L1 loss. So what it is it's quadratic near the origin, but at some point it shifts to becoming linear. One reason you might like this is because L1 is not differentiable at the origin, which sometimes causes problems in optimization. A nice thing about Huber is you're linear exactly when you want to be linear, meaning that when you move far enough away from the origin, you might have an outlier, and that's when you become linear. And taking that to the extreme, there's the Tukey loss function, which is quadratic near the origin, and then at some point it just shifts to becoming flat. Okay, so these are all special cases of what are called M estimators in statistics. And you can imagine casting the regression problem as instead of minimizing the squared loss, finding the vector x star that minimizes the sum of M function losses. Okay, so what I mean by this is the sum of there's some function M applied to what you predict minus what you preserve. What you observe. Okay, so you want to minimize this this loss function, and there's a bunch of work on sketching to do this. So again, there's a sketch which in input sparsity time can reduce this a large problem to a polynomial in d over epsilon sized instance of the same problem. It's actually a weighted version of the original problem. But typically algorithms for the original problem can handle non-negative weights, which is what this sketching produces. Yeah, okay. Here is the sketch, which we call an M sketch. It actually doesn't depend on your choice of M function. So the same sketch can be used for all of these M estimators. This matrix, what it is it's a block matrix. Okay, so it has order log n blocks. Each block is a product of two matrices. Okay, Si times Di. The Si's, they are the count sketch matrices that we went over before. They have poly d log n rows. Remember, there are these matrices that are super sparse. Okay, every column single non-zero entry, and a small number of rows. The Di are diagonal matrices. Okay, so Di, what it looks like is it's diagonal, and on the diagonal, it has some ones and some zeros. Okay, that's it. And so when I apply Di to a vector, I'm just zeroing out some of its coordinates. Okay, and what I is indicating is D0 is the identity matrix. I don't zero out any coordinates. And D log n is the zero matrix. I zero out everything, and there's no reason to go any further. And in general, Di zeroes out, or rather it retains roughly a 1 over D log n to the I fraction of coordinates. Okay, so you're more and more aggressively subsampling as you go down the blocks. You also have to rescale everything by D log n to the I. So if this is Di, you could equivalently think of it as, these ones being D log n to the I. Okay, this is just to preserve expectations. Let me give you an example in a moment. Yeah, so for the example, let's look at the L1 loss function. A very basic property that you might want out of your sketch, T, is that when you apply it to a vector, you roughly preserve the one norm. right? Now we want to apply it to regression, so we have this harder task of preserving the cost of every possible solution to regression. But let me just give you intuition for preserving the one norm of a single vector y. And in this example, y, it has one very large coordinate, n, and it has n minus 1 small coordinates that are all 1. And so the one norm here is 2n minus 1. And so it's roughly 2n, and it has two scales that matter, right? It has this single heavy coordinate, and it has many, many light coordinates. And to estimate the one norm, you kind of have to, up to a factor better than 2, you kind of have to observe both scales. And that's what these blocks are doing. So if you look at the top level, this top block, D0 is just the identity matrix. So S0 is a count sketch. And what's going to happen in a count sketch, I have a small number of buckets, and I'm throwing, n goes to some bucket. You might get scaled by plus or minus 1. And all of these other coordinates 1 also get thrown to buckets. And I get a bunch of plus minus 1s here, plus minus, I'm adding them all up in all these buckets. But the important point is these plus minus 1s, they're going to concentrate to something around, plus minus root n. And so all of these buckets are going to be very small. They're going to be plus minus root n, except for this one bucket that contains this very large coordinate. And so I detect this large coordinate at this very top level. And what about these small coordinates? Well, it's hard to figure out how many of them there are at the top level, but there will be some level of subsampling by these diagonal matrices di, for which I roughly sample one single item. And with very high probability, that item is going to be one of these n minus 1 coordinates. And so what's going to happen is one of these coordinates is going to survive, and then I'm going to scale back up by n. It's 1 divided by the probability that I sampled the coordinate. And therefore, I sort of estimate both of these two scales. Okay, so that, when this one coordinate survives and it gets hashed to some count sketch bucket at that scale, it's totally okay at that point because no one else has survived, so it's just sitting here by itself, and it's not corrupted by noise. That's how I can detect the light coordinates. And in general, you have to handle all scales of coordinates, and that's what this sketch does. There are other sampling-based strategies as well, not just sketching, that give similar guarantees for robust regression. Okay. So yeah, let me move on to yet another variant of regression, kernel regression. So here you're given endpoints x1 through xn, and they don't really exhibit a linear structure. I'm being vague about that, but what is good to do to these points is to apply some mapping to them, a nonlinear mapping phi to them, to lift them to what's called a feature space. Okay, so here is an example, the polynomial kernel of degree q. And here's the mapping. I have some point in r to the d, and I'm going to lift it to some super high dimensional space, a d to the q dimensional space. And the way it works is, well, I take my input point x, and the coordinates in the output are indexed by all q tuples of indices between 1 and d. Okay, so I have d to the q such tuples, and the coordinate value at one of these tuples is the product of the coordinates of x at those tuples. Okay, so here it's xi1 times xi2 through xiq. Okay, so this is sometimes your feature mapping can even be infinite dimensional. Here it happens to be finite, but it's very large. And sort of the hope is, well, maybe I should do regression on the lifted points, after having applied this feature mapping to them, because maybe there's more linear structure in this other space than there was in this original space. So regression doesn't work very well in the original space. And this polynomial kernel, one reason I mention it is it's very versatile in the sense that if you take other kernels and approximate them with Taylor series, for example, the Gaussian kernel, then the individual terms in the Taylor series are polynomial kernels of a certain degree. And so you can end up approximating other kernels with a polynomial kernel. And you can define a regression problem. And here is what's called kernel ridge regression. So you have this matrix A, which is huge. Okay, it's d to the q by n. And you would never want to write this down. Okay. And what it is each column is just the feature expansion of one of your endpoints. Okay, the first column would be 5x1 and so on. And the kernel ridge regression problem, you look at what's called the kernel matrix A transpose A, which is n by n. And you have a vector B, and you try to fit it to the kernel matrix. Okay, you try to find these coefficients y. And typically, you look at the regularized version where you add this ridge penalty that we're talking about. Okay, so here is kernel ridge regression. And I want to stress that you're just given the matrix A, right? So you don't have time to compute. Sorry, you're given the endpoints, x1 through xn. You don't have time to compute this matrix A, which is d to the q by n. So can you somehow use sketching to solve this problem? And you could also just explicitly compute this kernel matrix, but that would take a lot of time as well. I mean, that would take n squared d time. Can you solve this problem faster with sketching? And it turns out that you can. So there's this nice sketch called the tensor sketch due to Peg and Pham. And the way it works is as follows. So I'll describe it for sketching an individual vector. So I have a tensor product of q d-dimensional vectors, x1 through xq. In our polynomial kernel example, all the xi's are the same. And I want to sketch this down to a small number of dimensions, say k. The idea is, well, okay, let me apply a count sketch S1 to the vector x1 on the first mode, and apply an independent count sketch S2 to the vector x2 on the second mode, and so on out to the qth mode. Okay, each of these is an independent count sketch. And the okay, so each of these sketches only has k dimensions. And the nice idea behind Peg and Pham's work is that, well, let's look at the k coordinates of this vector and think of them as coefficients of a degree k-1 polynomial in some formal variable z. Okay, so I can write down a polynomial which is degree k-1, and the formal variable z, and the coefficient here is just the entry of this. If I'm looking at sj, xj, it would be the ith entry of that. Okay, so I write down some polynomial, and what I do with these polynomials is so I get a polynomial for each of these modes. I got q polynomials now, and what I do with these polynomials is I multiply them, and then I take them mod z to the k-1. Okay, I can do this very quickly using the fast Fourier transform to multiply polynomials. And so then I'm left with this new degree k-1 polynomial. And what is that? It turns out that actually, if you look at the coefficients of that polynomial, it corresponds to having applied a count sketch matrix to this d to the q dimensional vector. But it's a very particular kind of count sketch matrix where the hash function, instead of uniformly randomly choosing the location of a non-zero in each column independently, what it is I take these hash functions hj, what they mean, if I have a count sketch sj, remember I have a single non-zero entry per column. And here's the non-zero entry in the first column. I'm just going to call it like the hash function hj of 1. Okay, and the non-zero entry in the second column, it's at some other position hj of 2. Okay, and it has a value 1 or -1. In this case, sigma of sigma j of 1 is 1 because the sign is +1, and here sigma j of the second column is -1 because the sign is -1. Okay, all I'm saying here is that, you know, a count sketch can be represented by a hash function h and a sign function sigma, which tell you the location and non-zero and the sign on each column. And you know, you might choose these to be independently random for each of these individual S1 through SQ. What you end up getting by this polynomial multiplication is that new hash function where the value at one of these Q tuples is the sum of your hash functions on each of the count sketches mod k, the dimension here. And your sign function is the product of sign functions. And so it's very structured, but it turns out that there's enough independence here to still show all the properties you need for this sketch and solve paradigm to work for a number of problems. So, you know, the idea is A transpose A, you know, as we said, A is D to the Q rows, it's intractable, but I can compute S times A, where S is this, you know, this new count sketch. And, you know, to compute S times A, I do it column by column, but I never have to form this D to the Q dimensional column of A. I just, you know, do this procedure of sketching it Q times independently with count sketches, and then doing this convolution procedure and so on. So I can compute this product without ever materializing A. And so I approximate the kernel matrix with A transpose SA. And you can show that this this still gives you good solutions. There is one caveat here, which is this original proposal of tensor sketch. The dimension k actually needs to grow as 3 to the q. Now, q is the number of modes here. Remember, the order of your tensor. And while that's fine for some applications, like in natural language processing, sometimes q is 2 or 3. But when you want to approximate other kernels, like the Gaussian kernel, your Taylor expansion, sometimes you have to go out to log n terms or so, and this 3 to the q is going to kill you. And this is a real dependence. Okay, so you can come up with examples where this kind of sketch, you know, does have variance that is high, and you need k to grow as 3 to the q. And one thing that we did recently is we showed how to get a polynomial dependence on q. So it's a new sketch for high degree polynomial kernels. And it's based on a binary tree-like structure. So these are the, you know, if I want to sketch a fourth order tensor, I'm going to again apply count sketch to each of the individual modes. But instead of doing tensor sketch in one shot, what I'm going to do is I'm going to combine two modes with a q equals 2 tensor sketch. And over here, I'm going to combine two modes with a q equals 2 tensor sketch. And then I'm going to take those outputs and combine them with a q equals 2 tensor sketch. And by doing this in a binary tree-like fashion, you're able to actually reduce the variance. And now we can get a sketching dimension, which is polynomial in q, and therefore much more suitable for Gaussian kernel. But yeah, so, okay. Let me also mention another variant of regression that sometimes comes up, which is called tensor regression. So just go back to this vanilla version of least squares regression, where you know, you have an over-constrained problem here, and you know, what if your solution x star, it's d-dimensional, and you don't want to store d parameters? I mean, for whatever reason, maybe you're using this in some other system, d is too large. So one way of reducing the number of parameters in your solution is to restrict your solution to live on a manifold, to be drawn from some family of possible solutions, not all possible solutions. And one common thing is, well, let's say that our solution x, it has to have the form of a tensor product of two vectors. So suppose r is 1. This would just be u1 cross v1. So it's saying, you know, I'm only interested in solutions x star in r to the d, which have the property that x star can be written as u1 cross v1, where u1 and v1 are root d dimensional. The nice thing is I only need two times square root d parameters now to specify my solution. More generally, maybe you want the sum of r products of tensors, and then you only need 2 times r root d parameters instead of d parameters. So this, yeah, is called tensor regression to reduce the number of parameters. And so a natural question that you might have is, well, you know, if I don't have to preserve the entire solution space of regression now, I only have to preserve those solutions on this manifold, can I get by with a smaller sketching dimension? And it turns out that you can. And the sketching dimension, the number of rows depends on what's called the Gaussian width of the solution set, you know, which you may have seen Gordon's theorem for Johnson-Lindenstrass matrices. And it turns out that there are also sparse versions of this. So in this particular case, you can show that your sketch can have close to the number of parameters in your solution rows, so roughly order r root d dimensions instead of d dimensions. And not only that, the sketch S can be sparse, so it only has polylog d non-zeros per column. And so, yeah, there are lots of nice questions here about trade-offs between sparsity and dimension. This is just, yeah, another example.
Say something about how you actually solve the problem, even if you don't sketch?
Yeah, that's a great question. So what this sketching would do is reduce this problem to a smaller version of itself. But how do you actually solve the problem itself? And in this case, you know, you don't. There isn't a good out. I mean, so the way the algorithm works, practical algorithm works, is with alternating minimization. So what you would do is you would fix one of the things and solve for the other. But it's heuristic, or you have to make some assumptions for it to converge. Yeah, so you're reducing, you know, a large instance to a smaller instance and running the same heuristic on the smaller instance. Okay, let me also mention one final thing about regression, which is structured matrix regression. So another, besides sparsity, another thing that could help you with time complexity is that often your matrices A have special structure. So for example, your matrix A might be a submatrix of Henkel, Toeplitz, Vandermonde matrix, some matrix more generally that has low displacement rank. This is a family of matrices that come with very fast matrix vector multiplication algorithms, so like order n log n time. And so perhaps you can utilize this structure to get very fast algorithms. In fact, algorithms that maybe are even sublinear in the number of non-zero entries of your matrix. And this is in fact true. It turns out that there's a very general theorem that says you can solve regression in T of A log n time plus poly d over epsilon, where T of A is just the time needed to multiply A by an arbitrary vector. Okay, so, you know, T of A is always at most n and z of A, as we've seen, we have such algorithms, but it can actually be much less for structured matrices. And so then you can get these speedups. This uses a recursive leverage score sampling framework that I don't have time to get into, but it's a nice framework that actually reduces the problem to just a handful of matrix vector multiplications. Okay. That's all I wanted to say about regression. I'm just going to say a few things about the low rank approximation problem in the remaining 5 minutes or so. So low rank approximation, another very important problem in optimization. You have some big matrix, both of the dimensions might be large, and you want to approximate it by a low rank matrix. You know, it's easier to store. You can multiply more quickly by multiplying by each of the factors, you're denoising and so on. And the singular value decomposition, or SVD, it gives you an optimal solution for many norms. And the solution is just to take the SVD U sigma V transpose, U and V have orthonormal columns, and just truncate it, okay? So you take the top K singular values, you get sigma K, and you zero out everything else. As with regression, that also had a closed form solution, but it's slow. So, the natural thing to ask is, can you compute a good solution quickly? And we'll look at, say, the Frobenius norm, which is, entry-wise Euclidean norm. And it turns out that you can use sketching. So you can, instead of spending nd squared time to compute an SVD, you can use sketching to get an approximate, a 1 plus epsilon approximation in n and z of A, number of non-zero entries of A, plus n plus d times polynomial in the rank k that you care about, and 1 over epsilon. Okay, so n and z of A could even be close to n plus d as opposed to nd squared time. And let me just quickly tell you, what the idea behind sketching is in this context. So the idea is you have this n by d matrix A, and you think of the n rows as points in R to the d. Okay, here are my points in R to the d. And you compute S times A, where S is one of these short fat matrices. A could be square here. We're not assuming anything about n and d. S is a short fat matrix. So if I look at S times A, it's a very, it's a matrix which has a very small number of rows. Think of it as k over epsilon. K is your rank parameter, epsilon your accuracy. And I can look at the span of the rows of S times A. That's a k over epsilon dimensional subspace of R to the d. And I've drawn that here as a line. And the idea behind applying sketching for low rank approximation is take each of your rows of A and project them onto S times A. And now just do the SVD on the projected points. You still have n points, but remember SVD takes n times dimension squared time. But all of these points, they now live in a k over epsilon dimensional subspace. And this is where your savings is coming from. Now, why does it work at all? Well, you can think of S times A, it's taking random linear combinations of the rows of A. And so, if you have some large singular values, some directions that are very important for low rank approximation, well, they're going to stand out in these random linear combinations. Okay, those directions are going to be roughly preserved, and therefore you can show that this subspace, it actually contains a good rank k space inside of it to project onto. So that's kind of how the proof works here, and the n and z of A time just comes from the fact that you can compute S times A very quickly. Okay, so I'm going to skip. Oops. Okay, so just let me mention some quick other results on low rank approximation that can be derived with sketching. So just like regression, instead of least squares loss, you can look at a general loss function G, and sketching has been used to come up with entry-wise absolute value loss function low rank approximation. These problems are NP hard, but sketching gives you fast approximation algorithms and much wider class of loss functions. That's one thing I wanted to mention. It's useful for column subset selection, the column subset selection problem. Let me skip over the algorithm. And let me just say that sketching has been used for tensor low rank approximation. Here, there are lots of issues. The best rank k approximation to a tensor is not even well defined because of what are called border rank issues. Also, it's NP hard to compute the rank of a tensor. But there are various approximation algorithms and ways of coping with those issues. Another thing is weighted low rank approximation. Maybe you care about Frobenius norm, the sum of squares of loss function, but not all entries have the same importance. Maybe some entries have higher variance than others. So you want to do an entry-wise multiplication here with a weight matrix W. Another thing you might care about is structured low rank approximation. Someone gives you a matrix A and it's positive semi-definite. And so you want a nice positive semi-definite low rank approximation. And one nice thing about positive semi-definite matrices A, is the diagonal actually encodes a lot of information about the matrix. So if I take some off diagonal entry, its absolute value is upper bounded by the product of the two diagonal entries. And so this this is just because A can be written as B transpose. So the diagonal entries, you can't sort of hide a very large off diagonal entry. It'll be found by looking at the diagonal, and therefore you can design sampling schemes based on the diagonal and actually get nearly n time for solving this problem, even though the description size is n squared. And let me just wrap up. So yeah, sketching is used for a wide number of problems. CUR decompositions refer to a special kind of low rank approximation where the factors consist of actual columns and rows. It's used for k-means clustering. Since sketching provides compression, it's useful in distributed and streaming computations. It's useful for speeding up first and second order optimization. We saw an example with gradient descent. It's also used in the state-of-the-art, TCS linear programming algorithms. There is some recent work on trying to learn a sketch. So instead of just choosing a random count sketch, can I learn the positions of the non-zeros and the signs and get a better accuracy? And yeah, it's useful for other things, finding a latent simplex, sparse PCA, trace estimation. I won't get into those, but I have a monograph if you're interested in some of these problems, and I'm happy to talk more about it. Thanks very much.
Thanks a lot for a great talk. I will now open it up to any questions that anybody might have for the speaker.